Section 7.1, Roots and Radical Expressions. On our first slide, let's take a look at the syntax of a radical. Here we have our radical symbol. The numeral or variable inside the symbol here, represented by A, is our radicand, and the root that we're going to use to perform the operation is the index. When the solution has two real roots, which is a plus or minus, then the positive solution is called the principal root. The other root is called the negative root. Here we have the nth root. For any real number, a and b, and any positive integer n, if a to the nth power equals b, then a is an nth root of b. Well, let's take a look at that. Here we have 3 to the 4th power equals 81. Then what we say is this is the 4th root, and here our radicand is 81, our index is 4, of course, our radical symbol, and that tells me that our solution is 3. If I have 5 to the 3rd power equals 125, then the cube root of 125 equals 5. Here, my radical symbol, my radicand is 125, and my index is 3. Let's recall, if I have 3 to the 4th power, that is 81. I know 3 times 3 times 3 times 3 is 81. And I also have negative 3 to the 4th power is 81. In other words, negative 3 times negative 3 times negative 3 times negative 3 is also 81. Therefore, when I take the 4th root of 81, my possible solutions are either a positive or negative 3. Therefore, if I have an even index, my possible solutions are going to be positive and negative. My positive solution is my principal root. On the contrary, if I have an even index and my radicand is negative, I do not have a solution. It's not possible to perform that operation because a negative times a negative is always a positive, or a negative times a negative times a negative times a negative, which is to the 4th power, is also positive. Anything to the even power is going to have a possible solution. Therefore, this is not possible. But if I take a look at the other side of the line, I have 5 cubed, which I know is 125. 5 times 5 times 5. I also have a negative 5 cubed. A negative 5 cubed is going to give me a negative 125. Negative times a negative is positive, and a positive times a negative is negative. Therefore, I have 2 setups, just as I have shown here, with the 5 times 5 times 5 and negative 5 times a negative 5 times a negative 5. Therefore, I know if I take the cube root of 125, I do have 5. 5 times 5 times 5. But I can also have a cube root of a negative 125, which is a negative 5, because a negative 5 times a negative 5 is positive, but times a negative 5 is a negative 125. Therefore, I can have an odd root with a negative radicand and have that be possible, as demonstrated above. So if I have an odd root, I can have a solution that is either positive, or I can have a solution that is negative. Let's take a look at this chart. This is the type of radicand I have, whether it's positive, whether my radicand is 0, or whether my radicand is negative. This is if my number of nth roots is an even index, and number of nth root is an odd index. If I have a positive radicand and an even index, I have 2 solutions, one positive, one negative. If it is 0, the square root of 0 or the 4th root of 0, my solution has one possible value, which is 0. If my radicand is negative, I cannot perform that operation. Here, if I have an odd index and my number is positive, I have one solution, a positive principal root. If my radicand is 0, again, I have one possible solution. Cube root of 0 would be 0, for example. If I have a negative radicand, again, I have one possible solution, as we have on the previous page, which would be the cube root of a negative 125 is just a negative 5. In this property, the nth root of a to the n, where a is less than 0, I have the nth root of a to the n. The solution is the absolute value of a, where the exponent of that value is odd, and that is when n is even. I need to ensure that because the nth root is positive when x is negative. Remember, I can't have a negative radicand, and that ensures that value. Let's look at some examples. Here I have the square root of 16x to the 10th. I know the square root of 16 is 4. And to determine an nth root of a variable with an exponent, I just take that exponent divided by the index. So here the index is 2. 10 divided by 2 is 5, so I have x to the 5th. Or in other words, when I find a product of variables, I add their exponents. X to the 5th times x to the 5th is x to the 10th. And since this value, which would be my a here, has an odd exponent, I need to make sure that this is inside the absolute values. That ensures that the nth root is positive when x is negative. Our next example, I have the cube root of x to the 6th, y to the 12th. Again, x to the 6th, or the exponent divided by the index, is 6 divided by 3, which is 2. Or in other words, x squared times x squared times x squared. To add the exponents when I find the product of variables gives me x to the 6th. And y to the 12th divided by 3 is y to the 4th. And here, I don't need to have absolute values, because if a is negative, then the radicand is negative, and the root must also be negative. In our next example, I have the fourth root of 81, a to the 4th, b to the 8th, c to the 12th. The fourth root of 81 is going to give me 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. A to the 4th, and the fourth root of that is going to give me just a, or 4 divided by 4 is 1. A times a times a times a is a to the 4th. B, 8 divided by 4 is b squared. And c cubed. And I'm going to rearrange this where my odd exponents have to be in my absolute value. 3 b squared a c cubed is inside my absolute values. On this example, I want to simplify radical expressions with variables. On these examples, my index may not divide evenly into the exponents. To do that, I need to use our product of exponents to get that index to divide in evenly. Let's take a look at the first example. I have the index of 2, or the square root of L to the 4th, M to the 5th, N to the 7th. I know that I can have these variables simplify. In other words, I can leave L to the 4th as it is because I know 4 divides by 2 evenly. M to the 5th, the 5th power does not divide by 2 evenly, but by the product of our exponents, I can actually get that to happen by using M to the 4th times M. I know that M to the 4th times M is M to the 5th, and 4 plus 1 is M to the 5th. Therefore, I know that I can simplify this under the radical. Again, I can do the same with N to the 7th. That gives me N to the 6th times N. Now, all the exponents that are going to be divisible by the index will come out of the radical, and the others will stay inside. So let's take a look. I have an even index, so I'm going to have L to the 4th. The square root of L to the 4th is L squared, or L squared times L squared is L to the 4th. M to the 4th is M squared. And notice those will be taken out of the radical. And I have N to the 6th, which is going to give me N cubed. N cubed times N cubed is N to the 6th. What's left inside the radical is M N. And my odd exponents will have to be inside an absolute value, as for the property in the previous slide. On this example, I have the cube root of a negative 8, x to the 17th, y to the 5th, and z to the 19th. Let's simplify these expressions inside, or break them up into products in such a way that the exponents are going to be divisible by 3. That's going to give me x to the 15th times x squared, y to the 3rd times y squared, and z to the 18th times z. Then I can simplify and take out what's needed. The cube root of a negative 8 is a negative 2, and that comes out. The cube root of x to the 15th is x to the 5th. The cube root of y cubed is y, and the cube root of z to the 18th is z to the 6th. And what's left stays inside the radical, which is going to be x squared, y squared, and z. And recall, our index is 3. On our next example, we have the fourth root, and we can simplify inside that radical to make this problem simplify even further. I have 16, a to the 20th times a, b to the 8th times b squared, and c to the 8th. When I simplify, I have the fourth root of 16, which I know is 2. The fourth root of a to the 20th is a to the 5th. The fourth root of b to the 8th is b squared. And the fourth root of c to the 8th is going to be c squared. And that leaves inside the radical the fourth root of a b squared. Since this has an even index, I have to put absolute values around my odd exponents. That gives me 2 b squared, c squared, a to the 5th, inside my absolute values, and the fourth root of a b squared. On this example, they want me to find all real square roots of each number. Here I want the square root of 144, which I know is the plus or minus of 12. Here I want the square root of a fraction, 9/25. I take the square root of the numerator, which is 3, the square root of the denominator, which is 5, and since it's a square root, that's a positive and a negative. I cannot take the square root of a negative radicand, therefore here I have no square root, or none. And last, I have the square root of 0.0064, which I know is 0.08, and since I'm taking the square root, that is a positive and a negative. On this example, I want to find all the real cube roots of each number. The cube root of a negative 8 is a negative 2. A negative times a negative is a positive 4 times a negative 2 is a negative 8. The cube root of 0.125 is 0.5, positive. And the cube root of a negative 1,000 over 64, take the cube root of the numerator, which is 10, the cube root of the denominator, which is 4, and of course that is negative. Next, I take the fourth root of each number. Here I want the fourth root of a negative 81. I cannot have a negative radicand with an even index, therefore here I have none. On the next one, I want the fourth root of 81, which is going to be 3. And of course, since it's an even index, that's a positive and a negative. And the last one, I want the fourth root of 0.0012 or 0.0016, which is going to be 0.2. And of course, that's going to be plus or minus. On this example, I want to find each real number root. Here I have the square root of 25. The real root of the square root of 25 is 5. Next, a negative square root of 49. The real number root of the square root of 49 is 7, and I bring down the negative, negative 7. Here I have an even index with a negative radicand, therefore I have no real root. I cannot have a negative radicand with an even index. My last one, the cube root of a negative 125, the real root of that is a negative 5. On this example, simplify each radical expression using absolute values when needed. Here I have the cube root of a negative m to the 15th. Recall when I have an radicand with a variable with an exponent, I'm going to take that exponent and divide it by the index. That gives me m to the 5th. And since this is the cube root, I can have a negative because a negative times a negative is positive times a negative is a negative. And m to the 5th times m to the 5th times m to the 5th, adding the exponents gives me m to the 15th. Here I have the 4th root of 625 x to the 8th y to the 4th z to the 15th. I do have 625 as the real root being 5 for the 4th root of that. I can take the 4th root of x to the 8th and y to the 4th, but I need to simplify z to the 15th. So I bring down my radical expression to the 4th root, and that's going to give me 625 x to the 8th, y to the 4th, and z, and I'm just going to subtract that by 3 to get 12, and that would give me z to the 12th times z cubed, which is z to the 15th. Now let's take the 4th root of what I can. The 4th root of 625 is 5 x squared y z cubed, and what's left inside is going to be z cubed. And recall, I need to put absolute values around my variables that have odd exponents because I have an even index. That gives me 5 x squared, absolute value of y z cubed times the 4th root of z cubed. Again, I want to simplify each radical expression using absolute values when needed. Here I have the 5th root, and I can simplify on the inside to make sure that I can take the 5th root of all my variables. Rewrite the radical to the 5th root, the index, negative 32. That would be x to the 5th times x cubed, y to the 10th. I can take the 5th root of that, and z to the 25th. I can take the 5th root of that. Therefore, the 5th root of a negative 32 is a negative 2. X to the 5th, 5 divided by 5 gives me x to the 1st. X cubed will stay in. Y to the 10th, 10 divided by 5 is y squared. Z to the 25th, 25 divided by 5 is z to the 5th. That gives me the 5th root of what stays in the radical is x cubed. Here I don't need to have any absolute value symbols because my index is odd. Next I have the 4th root of 81 a to the 36 b squared c to the 24th. Here I don't need to simplify any further. On my 4th root of 81 I'm going to have 3 a to the 36. 36 divided by 4 is a to the 9th. B squared will stay inside the radical. And c to the 24th, 24 divided by 4 is c to the 6th. And then since I have an even index, I need absolute values around my odd exponents on the outside. 3, c to the 6th, absolute value of a to the 9th, the 4th root of b squared. On my next example, again, I want to simplify each radical expression using absolute values when needed. To take a look at this one, I have an expression that is to the 4th power under an index of 2. So I have the square root of the quantity of 2x minus 3 to the 4th. What I can do is let y equal 2x minus 3. Now when I substitute in, I can take the square root of y to the 4th. And when I take the square root of y to the 4th, I know that that's going to be y squared, or 4 divided by 2, which gives me 2. Now I can substitute back in, which would give me the real solution, which is 2x minus 3, and that quantity would be squared. I can either follow this route of substitution or go directly to the solution. Here again, what I want to do is, knowing that I have an index of 2 to the n, and I have an exponent with 8 to the n, all I need to do is take that exponent divided by the index, 8n divided by 2n. The n's will cancel, leaving me x to the 4th.